Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to week 4, lecture 4 of dynamic atomic force microscopy methods. In the last class, we'd been talking about the quartz tuning fork sensor and how it provides an alternate platform to achieve high-resolution AFM and force spectroscopy in addition or in complement, let's say, to the traditional silicon-based cantilever probes. In particular, we talked of two possible configurations, where the two tines of tuning forks are free, and the other one where you might fix one. In either case, you would use these kind of probes to approach the sample, measure frequency shifts as a function of z, and then use the formulas that we have already discussed, such as the Sater-Jarvis method or the matrix method, to invert those frequency shifts to reconstruct the conservative interaction forces as shown on the right. What we're going to do today is to step back and take a long-term view of, from the inception of atomic force microscopy to where we are today. How has frequency modulated AFM or FM-AFM evolved in its ability to see features at extremely high resolution? In particular, when the atomic force microscope was invented, very soon after that, there was a rush to try and demonstrate that the AFM could actually achieve true atomic resolution and achieve the kind of resolution that scanning tunneling microscope had already shown and demonstrated before. And this was very hard to do. Nonetheless, very soon after the invention of the atomic force microscope, just a few years after in fact, the first images where there was, let's say, clear atomic periodicity observed, those images started coming out, and all those initial images that demonstrated atomic periodicity were actually based on contact mode AFM. Now, you may recall the contact mode AFM works in the principle of it's a static AFM mode. You apply a constant force, and you move the base of the lever up and down to keep the force constant as you scan over the sample. What you see, for example, on the top left is one of the earliest contact mode images that show atomic periodicity. This is of a lithium fluoride 001 surface, and the bright spots are protrusions in the topography, which they correlated with a model of the lithium fluoride surface and attributed those to the fluorine ions, and the rest would be the lithium ions and so on. So what was interesting about this image was that it was taken at a force, applied force of about 10 nanonewtons. And of course, all these experiments to achieve atomic resolution in the early days required one to operate not only at cryogenic temperatures, but also certainly in ultra-high vacuum. The reason one needed to do ultra-high vacuum is really to make sure that the surfaces were absolutely clean, so that the imaging tip could truly encounter the actual atoms on the surface and actually probe around and feel effectively the actual topography of the surface without polluting or without having other things disturb the surface. Very soon after that was the first atomically resolved image, or certainly an image showing atomic periodicity of potassium bromide 001 in contact mode. This came out of Giesebel's group, and sure enough, here you see two kinds of protrusions. One was attributed to the bromide ions and the other to the potassium ions, and so on. Very soon after that, there was one of the earliest images taken in water, which demonstrated atomic periodicity using contact mode in water. Also came out of Binning's group. Even here at Purdue, going back in those early 1990s, Ron Reifenberger's group was also pursuing contact mode scans in UHV conditions, trying to get atomic periodicity in images as shown on the bottom right. The key point is all these initial efforts at trying to get atomic resolution. Today we recognize that all these images were what we today call quasi-atomic resolution. The reason being that many of these images taken, do not show atomic defects. They tend to show perfect periodic arrangements, which in many of these surfaces is not very likely to happen. The second important thing is the forces applied were rather large, typically 1 to 10 nanonewtons, which suggested that the mechanism or the physics by which these images are formed would not lend itself to an explanation which suggested that you would have a single atom kind of probing the atomic structure of the surface, but rather at a force of 1 to 10 nanonewtons, the whole tip would be pressing against the surface and you would have multiple points of contact. And effectively what one would be doing would be to sort of not looking at the actual topography of the surfaces, but rather some sort of effect that comes out of multiple tips, multiple asperities that could be contacting at the same time. So the lack of observation of point defects was considered, one main reason to try to think of or try to consider other ways by which you might actually achieve what would be called true atomic resolution. So, going over some of the key disadvantages or issues, let's say, with trying to do atomic resolution imaging with contact mode AFM are listed here. From the early days, it was recognized that if you're doing contact mode imaging, you want to stick with non-reactive surfaces like many of the ones that I've shown you before, which ensure that the silicon tip or whatever tip material you're choosing for your experiments does not have very large chemical forces between the atoms on the tip and the atoms on the surface. Because the larger those attractive forces are, the larger the force you're applying on the sample, which would damage the tip, and then you would lose atomic resolution. So many of those initial studies were on chemically inert surfaces, which brings up the question about how could you get high resolution on reactive surfaces such as silicon 111. The second point I already raised that at these forces, one is likely to have multiple tips touching the surface. The third important question that came up is, what's the right kind of cantilever that you would need to get to atomic resolution imaging in contact mode AFM. And here there's a very important compromise that softer levers would allow you to detect the deflection better because they would deflect a lot more. But at the same time, softer levers would snap into the sample, and in the snap-in, the tip could get damaged during the snap-in. And if you're trying to achieve atomic resolution, you want to have perfect tips as you scan the sample. On the other hand, if you choose very stiff tips, you don't get much of a deflection, and as a result, the signal-to-noise ratio would become very poor for contact mode AFM, and as you're scanning the surface, small thermal drifts would then start corrupting the data. Now, to get over this problem of, the tip sample snap in and how it might damage the tip when you do contact mode AFM, some early experiments, like I showed you, tried to do contact mode AFM scans in water where the adhesion forces are significantly reduced. So this was one action, one way to try and circumvent this shortcoming. The other point that I raised in the previous slide was about the lack of initial images that showed point defects. And very soon that started being attributed to the fact that in contact mode AFM, as shown on the top right, one really has a situation where you have a very sharp asperity. I mean, you're looking at the atomic resolution, you have to consider the spatial periodicity in lateral forces that arise due to the arrangement of the atoms. So when you're scanning the surface, you're also basically applying a lateral force, and that you can get a stick-slip kind of a phenomenon, where as the tip scans over an atom, the lateral forces kind of hold onto the tip until a certain lateral force is exceeded and they snap over to the next sticking point, and so on. So when this process happens, one would expect not to actually see the actual height of the sample, but rather some sort of a convolution of this stick-slip mechanism, which could very easily mask the presence of point defects in the sample, which would then lead to atomic periodicity in the images that was due to the stick-slip events rather than to the actual topography of the sample. The other major issue that came up is if one is trying to image layered material, one could imagine situations in a contact mode that a small flake of a layered material, just a few atoms wide, could attach itself to the tip. As a result, you would have the situation shown on the bottom right, where you have actually a little flake that's scanning over the surface. This again would completely mask the presence of point atomic defects. And lastly, it was very hard with the contact mode AFM to really look at reactive surfaces, because the interaction forces between silicon tip and reactive substrates would be rather large, resulting in large forces and a natural inability to see atomic resolution images. So if it's not going to be contact mode AFM, how about dynamic AFM methods? And the first example I want to put up here is the question of amplitude modulated AFM or tapping mode AFM. And the first atomic resolution image of using tapping mode AFM was taken much later after the first such image was taken in FM-AFM. Actually, this was done in 1996. It did become possible to get atomic resolution with tapping mode AFM. However, it required very stiff cantilevers and extremely small oscillation amplitudes to accomplish. Generally speaking, the use of AFM for getting tapping mode AFM for getting atomic resolution images has been a difficult task, and there are very few works in the literature that have been able to show atomic resolution images of tapping mode AFM in comparison to the frequency modulated AFM approach, where there are hundreds of papers showing atomic resolution, true atomic resolution. So there are a few reports on the use of tapping mode AFM for atomic resolution in vacuum, but none in air. And more recently, there have been results that have been coming out on the use of tapping mode AFM for atomic resolution in liquid environments, as shown on the study on the right. So this brings up an interesting issue. Why is it hard to get atomic resolution with tapping mode? And there are many reasons which we can't go into detail at this point, but the reasons include, amongst other things, the sensitivity of the observables in tapping mode AFM to the tip sample interaction forces. It also needs consideration of the fact that the settling time in tapping mode AFM is actually different from frequency modulated AFM because of different feedback loops in the process. It has to do with imaging bandwidth, stability, and so on and so forth. So the use of AM-AFM is typically not considered the standard approach to look at atomic resolution on surfaces. So when it came to the use of FM-AFM for getting atomic resolution, the real breakthrough was made in 1995 with this publication that came out of Giesebel's work in Germany. And the idea or the potential advantages of using FM-AFM for doing atomic resolution images are listed on the top. One important benefit that one could get out of it was the fact that there's a 1 over F noise in all AFM systems, and by operating in the dynamic mode, one could operate at a frequency that was larger than the roll-off frequency of the 1 over F noise. As a result, one could circumvent or separate or not be affected by the 1 over F noise. The other important thing was the force sensitivity of FM-AFM is so high that one could actually operate with a stiff cantilever in the attractive regime or slightly repulsive regime without applying very large forces. So one could ensure basically that the tip doesn't really crash into the sample, that it's a very gentle probing of the surface that allows us to get atomic resolution. The last important thing is the principle of FM-AFM, in fact, indeed of all dynamic AFM methods, is that they tend to sense gradients or weighted versions of the gradients of the tip-sample interaction forces, which tends to increase the sensitivity to those forces that actually change spatially over the sample. So when you look at this image, this is the first image taken with non-contact AFM or FM-AFM of silicon 11177 reconstruction, and this is a very important result because the scanning tunneling microscope had solved this problem a few years ago and had resolved the actual structure, and this was the first proof that force microscopy could also do the same, get the same results. Now, when you look at this image, what you see are a couple of things really jump out at you. The first is that most of the image is actually foggy. It seems that you don't really see much. And so in this particular image, Gazebel was scanning, and over the first quarter, top quarter of the image, one really didn't see anything. It was foggy in some sense. And then all of a sudden, for about 5 or 10 scan lines, suddenly the atoms popped out on the surface that you see in the band where you see the structure of the surface. And those few scan lines, maybe half a dozen, maybe 10 scan lines, were just enough to map 1 unit cell of the silicon 111 surface. Very soon after that, going down the scan, this resolution was lost again. And then later, as you go to the bottom half, one sees a very different structure. One sees some sort of periodicity, but one doesn't see single atoms as one saw in that little band up there. So this was a pretty remarkable image. At the time, it was very hard to try and get these kind of images, and the idea that one could actually start seeing atoms at super high resolution was a big breakthrough using FM-AFM. The reason for why there is so much variability in these images was attributed to the fact that, in order to see atoms, you literally have to have, an add atom on the end of your tip probing the atoms on the surface. So in other words, the actual tip that's probing the surface needs to be an atom. You cannot have multiple atoms that are sitting out and interacting with the substrate. And so when these kind of images were taken, the tip itself is constantly undergoing or some transformations, and the atomic structure of the tip might actually change. You might go into a region where a single tip is actually imaging the surface, and that single tip, which is basically an add atom that's coming out of the surface, might have gotten removed, and another set of another structure of atoms with multiple tips may have come out, which would lead to entirely different images. So this really showed that the tip geometry, and by tip geometry I mean literally the last few atoms that actually probe the forces, are very important and critical to getting atomic resolution. So very soon after this FM-AFM result, the literature started flowing in on images taken with atomic resolution with FM-AFM. On the top left is, in 1995, the same year where Gazebel's science paper was published, was one of the earliest studies of atomic point defects using FM-AFM, in this case on indium phosphide. And very soon after that, on the top right, further FM-AFM images came out. I'd like to highlight one on the top right, also out of Morita's group in Japan, which kind of demonstrate an interesting principle in FM-AFM, in that the images that you see going from left to right are images of the same area taken with different frequency shifts. Remember, when you approach a sample, the frequency shift becomes negative, reaches a maximum negative value, and then turns around. So if you image with a small value of negative frequency shift, or a little negative frequency shift, the tip doesn't come very close to the sample. If the frequency shift becomes quite negative, that means the tip has come much closer to the sample. But if the frequency shift turns around and becomes positive, that means the tip has come so close that it's actually touching the sample, and we don't want that to happen. But what this shows is that the delta F at which you image at can be thought of as a focusing knob on your instrument. That if you do very small frequency shifts, you don't get to see the atoms. As you increase the frequency shifts, make them more negative, the tip starts coming much closer to the atoms. And at a key range of frequency shift values, in this case delta F minus 70 hertz, suddenly the atomic resolution becomes visible. So it's like a focusing knob. Very soon after that, the first images of biological molecules with FM-AFM were taken, this time double-stranded DNA, shown on the bottom right, where we know that we expect to see a helical structure of the two strands of double-stranded DNA. And by looking at these images were taken in vacuum, one can sort of see that structure coming out. Finally, some of the more interesting results concerned with high resolution in FM-AFM are related to this work that came out in 2000 out of Giesebel's group again, where images were taken using FM-AFM of silicon-111 surfaces using a tungsten tip. What was observed here was that if one zoomed in on the image of one particular atom, one could see that the surface of the atom was actually, the topography of the atom did not have spherical symmetry, but rather seems to show two crescent-like structures. And this brought up an interesting question. How is it possible that there might actually be a modulation of the height within an atom? Where does that come from? This is entirely unanticipated because silicon-111, one expects to see one unpaired sp3 orbital sticking out straight out of the perpendicular to the substrate, which would then result, if you had a normal tip, it would result in a nice circular symmetry of the image that one acquires. In this work, Giesebel attributed this crescent-shaped asymmetry that comes out to the fact that tungsten tips actually have two dangling orbitals, which could result in an image that causes an asymmetry between, due to the presence of, the asymmetric structure of the interacting orbitals with the orbital on the surface. This, of course, was pretty remarkable because it suggested that one is not just getting atomic resolution, one is getting subatomic resolution. And for the first time, perhaps it may be possible to image the charge density within an atom. Of course, this was a very controversial result, and there have been many groups that have talked about the possibility of the potential that this might arise due to other artifacts. Nonetheless, this was one of the studies that really opened the door to the possibility that subatomic resolution imaging is in fact possible. And further studies are ongoing in this area, and we hope to see some interesting results pretty soon. Lastly, I'd like to bring to your attention the fact that FM-AFM has also been used in liquid environments for getting atomic resolution. In the early days of FM-AFM, the natural reaction for a scientist, if they were asked, why do you get high resolution with FM-AFM, would be because of the high Q factors and because when you do phase detection, when you do phase locked loops, they're much more effective at detecting frequency shifts. And that frequency shift detection is a natural, better way for detecting forces than amplitude shifts might be. But using cantilevers in water means that the Q factors really decrease a lot, and we're going to talk about this in the last week of lectures, last week of classes in some more detail. So, big question that arose with this finding that came out of Fukuma's and Yamada's, Professor Yamada's group in Japan, was that you could operate in low Q environments and using FM-AFM actually get true atomic resolution, in this case of mica, in liquid environments. So with that, we'll end this lecture, and in the next lecture we'll continue talking about other results, but focusing on force spectroscopy using FM-AFM. Thank you.